Hello and welcome to another podcast. So this is still early in the course. This is bond line representation. It's the start of chapter 2 in our material. And let me go ahead and get rid of the floating screen. So if we can't see that, I'll get started on it. But what line bond representation means is a shorthand way of drawing chemical structures. Because if you draw all the carbons and all the hydrogens, you'll run out of ink in your pen, you'll run out of lead in your pencil, too much to write. So as chemists, we have a lazy way to draw things that just saves lots of time, and you end up using it also in pretty much most of biochemistry and many of your biostructures. So what it basically is drawing this exact thing you have drawn here, this 1, 2, 3, 4, 5, 6 carbon species with all the appropriate hydrogens on it. So this is known as a molecule as hexane. So hexane meaning it's an alkane, everything's sigma bonds. Hex meaning 6, so 6 carbons. But it gets redundant to draw all these H's. That's 14 things I don't need to draw if I just know that every carbon makes 4 bonds. And if it doesn't, if it has 1 bond to carbon, for instance, then it must have 3 H's. Or this carbon here has 2 bonds of carbon, so it must have 2 H's. So it gets kind of redundant to draw all the H's. It's just a lot of work, and we just know they're there. And then also, even drawing the carbons, if we just say that if there's a carbon here and carbon here, carbon here, carbon here, then maybe we don't need to draw the C, just a point, a point, a point. And that's basically what this comes down to. So here's the step-by-step process. We're going to first off ignore the H's. We're going to assume they're just there. So if I see this structure, C dash C dash C dash C dash C dash C, that I am missing 1, 2, 3 H's. So this must be an H3, missing 2 bonds, so 2 H's, H2, 2 H's, so H2, etc. So the first thing I'm going to do is I'm going to get rid of the H's. And then what I'm going to do is I'm going to actually make an angle, because I know it's not linear with respect to sp2 or sp3, excuse me, in this case. sp2 also wouldn't be, but that requires a double bond. sp is the only one that's linear, and this is definitely not sp. There's no triple bond. So I'm going to look at this and say that, okay, it's slightly up. It's going to be slightly down, slightly up, slightly down, because bond angles should be about 109.5. Okay, so I'm going to rewrite this structure. Now note C going up to form a bond to this C, going down to form a bond to this C, going up to this C, going down to this C, and up to this C. So you still have 6 carbons, but they're now drawn in this sort of zigzag fashion. Okay, and the last thing I'm going to do is I'm actually going to just ignore my C's. I'm going to redraw it one more time. And this time, without a C here, just the end of the line. Without a C here, just the point where the 2 lines intersect. Without a C here, and so forth. So this structure, these altogether 20 letters and all these lines, has now been replaced by 1, 2, 3, 4, 5, 6 lines. So you have to get used to it. So again, the 14 bonds to H's we're not going to care about. The 5 bonds between carbons turn into 1, 2, 3, 4, 5 lines. So these lines are going to be drawn, but that's it. So let's try another one and realize this is just shorthand for how to write things. So in this case, I have 1, 2, 3, 4, 5 carbons in the chain, and then coming off the 1, 2 second carbon, I have another carbon with H's. So again, first step, let's ignore our H's. So when I get rid of the H's, erase them all there. So if I literally just did this, I'm going to just get rid of my H's. So as I'm sitting there erasing them all, not erase them well, but just you get the gist. Notice that when I erase them, this is what I get, this carbon backbone. So first step, ignore your H's. Second step, put in this little angular arrangement. But that's just for the backbone. This carbon here, we're still going to say go straight up. So basically, I'm going to pull this one down, and this one down to make the structure. So it's going to look something like this. So zigzag, up, down, and then stop drawing your carbons. So this right here represents this. I'm getting ahead of myself, but nomenclature-wise, this was hexane, we said. This one, the longest chain is actually 1, 2, 3, 4, 5. So this is known as pentane. but I need to emphasize it's 2-methyl. Sorry about this. Didn't give myself enough space, but 2-methyl pentane. I'm going to redraw that whole thing because I did a terrible job. So let me write it from the get-go. 2-methyl, meaning I have a 1-carbon species, 1-carbon fragment right there on a 5-carbon chain. So 2-methyl pentane. Room for one more. This one is 1, 2, 3, 4, 5 with the O. So 4 carbons in an O. O is a non-hydrogen atom, so I'm going to still count it in the zigzags. So I'm going to end up with something very similar. 1, 2, 3, 4, and an O. 1, 2, 3, 4, and an O. So it's basically going to be this arrangement right here without this carbon coming up. But again, erase all the H's, except we consider the OH as a group. So I know it's kind of goes against what the rules I'm saying, but we only get rid of H's on carbons. So CCCCOH, it'll be CCCO and then an H. But in the final ignoring of things, I'm going to do a double trick here. I'm going to get rid of the carbons like we did in other ones. O stays because O is a non-carbon atom. I want to emphasize it. But no need to draw this bond. We know if it's an OH, it's got to be that bond. So this is our shorthand for that. So getting used to representing this structure, which is known as 1-butanol. We call it 1-butanol because the OH is located on carbon number 1. This will be 1, 2, 3, 4 carbons with an OH. So all numbered as such. I call this one number 1 because it's closest to the functional group of interest. 1, 2, 3, 4. Okay, so that's our starting point. That's our process here. So we're ignoring our H's. We are then drawing the zigzag form and then ignoring our carbons. Ignore our H's, draw the zigzag form, get rid of carbons, stick line. Functional groups, you have to draw in. So this is where you may have ran into seeing this in bio classes. So for instance, you might have seen something like this. I'll toss this out here as just an example. Something like that. Which what that represents is a carboxylic acid where you have a carbon with a carbonyl, so acetyl bonded O and an OH, so that's a carboxylic acid. So the total carbon count is 1, 2, 3, 4, 5, 6, 7, 8. Did I do that right? 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So an 8-carbon long chain. So very similar to what we said in some of our previous lectures, that fatty acids, naturally occurring fatty acids in biology, are an even number of carbons. So it's typically a carboxylic acid group and then an odd number of carbons, because when you add the one of the carboxylic acid to the odd number chain, you'll get an even number. So this is naturally occurring fat. So you'll be reminded, we've already done line bond representation when we showed you some of those fats in one of the previous lectures. So again, just want to reiterate, the first 5, 6, 7, 8 lectures in this class could be done interchangeably in any sequence and order. So we already done some of these line bond examples previously, this being an example of it. Okay, so let's continue down this road. This one hand drawn because honestly, it's probably the way you're going to get it. So you draw, let's say, this compound, which is 1, 2, 3, 4 carbon. So it's going to be bute, whatever it is. Has an OH on carbon, let's see, 1, 2. So 2-butanol, so 3-bromobutanol. So our steps are number 1, ignore your H's, which I just did, or I'm doing right now. Erasing all my H's. And then draw the zigzag. So let me draw the zigzag. Then I get to put the Br and OH on there. So anything going up on an up point is like that. But the OH, I can't draw it this way because that angle is now less than 109.5. So it ends up, my OH is actually going to be pointing down. And then the final thing you do, you get rid of the carbons. and just make them line intersections. So this is going to now be this. So something like that. So I'm going to erase what I've drawn and have it come in picture-wise. So it's going to be clear in just a second. So you end up with this. And again, want to emphasize, you have to have reasonably large angles, 109.5, or this one ends up slightly higher than that, but you don't want small angles. So it's not this structure. Okay, so now we have to worry about hybridization when we do line bond drawings as well. So let me just emphasize, sp3 is a 109.5 angle, and here are my sp3 carbons. sp2 is 120. I have two of those. And then sp, which is 180, is this. So let me just reiterate, 180 degrees, 120 degrees, and 109.5 degrees. So I'm going to start with this represented bond right here. So I'm going to draw it in purple just to make sure I get this right. So carbon, carbon, carbon is now going to just turn into a triple bond. Connected to that will be this one carbon right here, and then this carbon right here. Connected to this one is sp3, so it's going to be bent. And then connected to this one will be another sp2, so it's going to be bent. And then sp3, something like that. Now, the beauty of it is I could have this one point up or point down, doesn't matter because sp3. This one does matter. So I've done something called a trans bond where it's on one side of the double bond here. So if I did an extending line through the double bond like this, these two carbons are on opposite sides. You'd have to traverse over that. So they're trans. They're across one another. I could have also drawn it like this, cis. And the thing is, I don't know which way to draw it because I haven't been given enough information. So nomenclature-wise, you'll have to be told that. So again, I'm going to erase everything, 3, 2, 1, and erase, and say that this is how it comes out. Now, again, this can be pointed up or down, doesn't really matter, but let me just double check. These two are sp3. These two are sp. These two are sp2, sp2, and then once again, sp3. So this one can rotate either way, doesn't matter, but this one we've drawn as trans. They're across the double bond from one another. Not, it doesn't matter that, like, in this case, it doesn't matter which way I draw it, but they will specify nomenclature-wise which one it is. Thing that definitely does matter, because the SP nature of this has to be linear. You can't have it bent like this. So this double bond is right, but this triple bond is wrong. Things have to come straight out from a triple bond. Okay, so bond line representation, not that challenging. You just have to practice with it. And the more you see things, the more you'll be able to practice. Let's go ahead and translate this one across. There's a ring in the middle. And then there's a group coming off of this carbon, OH coming off of this carbon. And this is a double bond connected to a pi bond coming around. This is not actually a ring. This H is separate from this O. They're not bonded. They're just drawn really close together, which is probably why we use bond line structure, because this gets really confusing right there. And even here, this is a little bit close and can get a little confusing. So I'm going to draw just this group at first. So it's a 1, 2, 3, 4, 5, 6-membered ring where you have alternating single, double, single, double, single, double bonds. So we'll start the middle ring and make sure I've done that correctly. So here I have this carbon. It has a double bond here, a single bond here, and an unwritten H. And then scooting all the way down to this carbon, it has a double bond here, single bond here, and an unwritten H. And then these two carbons have an OH and an OC3H I'm going to have to draw in. And then on the other side, these two carbons have respectively a carbon with a long connection of a pi bond, and then just an H, which I'm going to ignore. So I'm only going to be putting groups onto here, here, and here. So I'm going to get rid of my color coordination. Go ahead and draw what I can in. So again, I'm just going to have a bond here, and a bond here, because those are your non-H's. But where I have an H here, and an H here, I just ignore it. So up here, OH. We've done one of those already, so that's going to be simple and straightforward. This one, I can either draw as an O with a line, that's one possibility, or an O and a CH3, nomenclature-wise, or formula-wise. That's open to judgment call. Here, single bond to carbon, but here I have a double bond to carbon. I ignore my H's, and then this thing is pointing up. So because it is now cis, same side, these two groups are on the same side, I have to retain cis. I can draw this as CO2 OH if I want, or CO2H, the COOH, however you want to represent it. So I went ahead and did one way of doing it. We have an OH, OCH3, and COO2H. But you could have also easily drawn it instead as, instead of this group, I could have drawn it as OH. And I could have drawn this OCH3 group as, that would have been the same representation. So whether I draw the formulaic form, the lines, totally up to the person writing it. So if you want to draw it this way or the previous way, I'm going to click back to the previous way. That's also just as fine. Okay, going in the opposite direction, from a stick line figure to down here. And notice I've gone with the biomolecules, something called an antioxidant found in green tea. One of the things you hopefully start recognizing is patterns in chemical reactivity. When you see this six-member ring with alternating double bond, single bond, double bond, single bond, double bond, single bond, known as benzene. When benzene has an OH as well, when it has two OHs, it is known as catechol. And perhaps you've heard of catecholamines when you dealt with biomolecules, neurotransmitters. So usually with that, we have OHs on adjacent carbons, 1 and 2, as opposed to 1 and 3. But I'll just say the same thing. So catechin is a spinoff of a catechol. So this up here is a catechol. 1, 2 OHs next to one another. It's going to be called 1, 2, or ortho on a benzene ring, alternating double, single, double, single, double, single. Okay. So we're going to translate in the opposite direction. So I'm going to draw the ring system. So I'm just going to basically draw in carbons here, 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 here. So carbon, 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 six-member benzene ring, carbon, 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 six-member ring, benzene ring with a carbon check, carbon check, which is going off to there, and an O, which is part of that middle ring. Okay, now I'm going to put in my functional groups, and then at last my H's. So my functional groups will be an OH, and OH, and OH with this dashed wedge, which is colored in, I should say not dashed, but colored in wedge. And this dashed wedge going back to benzene. That's going to be something for a chapter coming up, but that's called stereochemistry, implying that a dashed line means it's going back or behind the board. Colored in wedge means it's coming out or coming in front of the board or in front of the page. So all your non-H's are in place. That was 1, 2, 3, 4, 5 OH's. And then H's. So H there, there, there. Should have 1 there. Should have 2 there. 1 and 1. So add in your H's. Added my 2 H's on this ring. So I need 2 more here and 1 here. And then I still need the ones on this ring. So the ones in this ring are in. And then last but not least, 1 here, 1 here, 2 here, nothing on O because it's set. Okay, so I feel like this has fallen into place. I mean, I can convert one way or another. So when we talk about chemical reactivity, mentioned before, OHs on benzene rings are very useful in terms of antioxidants, meaning they can react, they can undo the reaction of oxygen with some molecule in your body. So then they undergo redox chemistry. and really critical that you know what redox chemistry is. Simply put, gain H equals reduction. Gain O equals oxidation. Now I need to qualify this because if we gain H plus, we have reduced. So I should note gain of bonds to H by carbon, reduction, gain of bonds to O by carbon, oxidation. So I'm just shorthanding this, gain of H. So when I go in this forward direction, I'm going to notice I lose H's. This H is gone and this H is gone. So in the forward direction, it has been oxidized because I gained a bond to O. I went from one bond O to two, one bond O to two. So it is oxidative in the forward direction. The bracket around the O represents oxidation. And then in the reverse direction, it is reductive. It's been reduced. This bond line is so much easier to draw than drawing the whole thing out, but emphasizing that you went from one bond O to two bonds O, one bond O to two bonds O. Double bond was here. Now there's a new one here. Double bonds here and here. Those two are gone. So we'll go into how this occurred, but it's important because most of our mechanisms, most of our bookkeeping, our pathways will all center around this bond line methodology. Must know steroids, not for this class, but in your travels through bio, these are steroids that are very common. And I'm going to draw the bond line formation of it because that is going to be essential. That's going to be critical when you take biochem, take cell bio, molecular biology, any bio class. A lot of chemical structures we're going to draw this way. So this is a six-membered ring with a carbon, 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 carbon. They're all carbons because no other element drawn in there. Another six-membered ring, carbon, 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 carbon. Another six-membered ring, carbon, 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 and then a five-membered ring. Steroids have this same basic structure. It's called the androstenedione ring structure because it comes from an alkane without all these functional groups and without the pi bonds. It would be called androstenedione. So this is the androstenedione ring structure, meaning it's the same as androstenedione. Very common in bio to have this structural formation. This represents two bonds of O, nothing here, so two H's, nothing here, so two H's. Here, 1, 2, 3, 4 bonds, so it's set. 1, 2, 3, 4 bonds here, so it's set. This one must have an H. Two H's, two H's, one H, one H, two H's, two H's. O and OH in front, so an H in back. 1, 2, 3, 4 bonds, so this one's set. And two and two H's. So the carbons that are set and have all the bonds already drawn in, this one has 4 bonds, this one has 4 bonds, this one has 4 bonds, this one has 4 bonds. So I don't have to add anything. The ones with 1H will be here, 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 and here. The other ones are drawn in one that being 2 H's. Okay, so this is just good practice in figuring out what groups are going to have H's, line bond drawing. So testosterone, male sex hormone, responsible for, just to guess, physiological changes in the male anatomy. Estrone is one of a few different molecules that make up what's known as estrogen. So estrogen is the female hormone responsible for changes in the female anatomy, but there are different things that happen. So premenopausal and then pubescent, or prepubescent, postpubescent, and postmenopausal, or the periods, I should say, where this will have slight changes in what functional groups are on it. So I've just chosen one version of it, but estrogen is actually a series of compounds that actually literally evolves over time. And then progesterone, one of the hormones, again, in the female hormone cycle, and just so well studied, we know it inside and out as far as the structures of the molecules go. Note again that it's the same ring structure. So it represents, in this case, a benzene ring, single, double, single, double, single, double, which we saw before. Here, it's just the same as it was in testosterone, a 6-member ring, carbon ring with a double bond to O, and what ultimately going to call a conjugated double bond. But notice this structure is really similar. The difference being is this OH got replaced by this carbon with a double bond O, and an H in back, just like the H was in back there. So it's really not that much different. anyway, these are some of our hormones. And so I'm not saying you need to know these for this class. These are ones that I'm sure somewhere along the line, when you took a bio class, a cell bio class, reproductive physiology class, or a physiology class where reproductive processes kicked in, these structures also popped in. They had to because they're a major player in it. So just recognizing the bond line representation of biomolecules, you've had to do it already. You'll keep on having to do it as long as you do bio examples or take bio classes. So one that I want to emphasize, because this doesn't always get brought up in OChem and or bio, but icosa means 20. So icosanoids are 20 carbon species that end up having like oids, meaning some alteration of basic structure. So the fundamental structure, carbon 1 is a carboxylic acid. Here it's been deprotonated, so it's carboxylate. But it'd be carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it comes from a 20 carbon fatty acid, a long chain fatty acid that it's part of the whole prostaglandin cascade is what we're going to say. But when a cell gets triggered for whatever way, so let's say you cut yourself and you're exposed to oxygen, your cell membrane's exposed to oxygen, it will release a fatty acid that is just a straight chain of 20 carbons with a series of pi bonds in it. And so that starts this whole icosanoid or prostaglandin cascade. So some of the pi bonds originally ended up like every other, so to speak. So not quite every other, but double bond here. Then we'd have something like this, double bond here. Double bond would have been here, and then this one. And they do a chemical activity. We'll get into that in more detail towards the end of the semester when we start talking about carbonyls and alcohols. But the key thing here is recognizing how many carbons we're dealing with. So this is prostaglandin E2. So E simply represents somebody's recording of when they isolated these. So A was the first one they isolated, B second, C third. 2 represents the number of double bonds from the backbone that still exists from the original 4. So this still has 2 double bonds from the original 4, so it's a 2, not counting the carboxylic acid, so carbon-carbon double bonds. And thromboxane, if you know what thrombosis is, or you know what thrombin is, they both have to do with blood clotting. This is a molecule that triggers for blood clotting, meaning if you cut yourself, your cells get exposed to oxygen, your body will very quickly release this from the cell membrane. So you cleave it, it gets oxidized very quickly into various prostaglandins and thromboxanes that you need. This thromboxane gets released, it triggers for release of thrombin, which will end up cascading into a scab or just a coagulated repair network. Okay, so with that in mind, I want to just double check where things form. So it's important on this is knowing your numbers. So carbon number 1 is carboxylic acid. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So carbon 8 is key because that's going to form this ring. 9, 10, 11, 12. So here we have 8, 9, 10, 11. 12 has to go through an O. So it's still 12 here. So there's going to be my 8 and my 12. My 20 is at the end. I counted that one earlier, but here's my 8 and my 12, my 8 and my 12. So notice you have a double bond between 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6. You have a double bond between 13 and 14. You have an OH at 15. So all these are very similar in that sense. So you have OH is at 15. You have an O bonded to 9 and 11. O bonded to 9 and 11. 2 bonds O here at 11. 2 bonds O here at 9. 1 bond O at 11, 1 bond O at 9. So they're actually very, very similar structures. And as we get far enough into the class, I'm going to cycle back and talk about how these things are formed. But for now, we're just looking for structural similarities. So 9 and 11 become key players. 15 is a key player. So this is one of those things that at this point in the class, this is a moot point even looking at this. This is just trying to say cool numbering scheme. But for the future, what I want to get at is how these bonds are made, what redox things come into play. It's an oxidation reaction because I'm exposing to oxygen. There's a free radical involved in the formation of this group. And it just becomes just flat out really interesting how this thing works and how quickly it works. So prostaglandins are formed on command as we need them. So if you cut yourself, you don't want a hormonal response. You don't want some molecule released from a gland traveling through the bloodstream and hoping it targets the right spot. Instead, the right spot releases a prostaglandin, which ultimately sends a pain signal or a repair signal, a clotting signal, whatever signal you need. So it's local response. Examples are uterine contraction, heart muscle triggering, respiratory, like asthmatic response can sometimes be prostaglandin driven. So a lot of these things are local response, not just clotting like we have here, but just a lot of local messenger molecules. But the bond line method, the stick line method of drawing things, absolutely essential to recognize what this compound is. So two H's here, two H's, two H's, one H and one H because it's sp2 hybridized, these two carbons. It's cis, because I draw them the same side. And so the big thing I'm just trying to emphasize is, can you just, without like much effort, realize two H's, two H's, two H's, one H, two H's, one here. Can you fill in the missing H's in your mind and note that if this OH is going back, the missing H is in front. The O is going back, the missing H is in front. O is going back, so missing H is in front. This carbon's coming in front, so missing H is in back. And just get good at seeing things that aren't there. That's actually going to be one of the things that's highly expected of you. Okay, so that's it for our bond line. So thank you very much. And I will see you in class or at the next podcast. Thank you.